Let's look at this table, which is a comparison between the cache memory, main memory and the secondary memory, basis the features which are most important for our selection of any memory type that we are going to be using here. This clearly indicates that the cache memory is a very high speed memory, uses the random access method, the cost per bit automatically goes high because of the fast access speed. So let's look at cache memory and its organization and principles in more details right now. So the principles for cache memory, as I just discussed, was to give a higher upper end or upper hand on the speed of the memory, which is as compared to the processors. We want a large size but at the price of a less expensive memory. So instead of saving everything on the system or on the external device, we want something which is in between with the additional features and the qualities of both of them together. We want small amount of memory but which is fast. We would want it to be positioned between the main memory and the central processing unit, and we definitely want it to have a lesser or a reduced data access time. Let's look at this diagram. It is very clear that the cache sits between the CPU and the main memory. Look at the data that is transferred. We know between the CPU and the cache memory, it's a fast transfer because the unit that is getting transferred there is in the form of words. Whereas when we use a data transfer between a cache memory and the main memory, it becomes a little slower as compared to the other side because we will have a block transfer here. Now, we could also split this one single cache into multiple levels of cache at level 1, level 2, level 3 to reduce the access time. We will take these level 1, 2 and 3 a little later while I go in details further ahead. So, we have seen the multiple caches here. L1 cache, this is usually inside the CPU or because it's the fastest and the smallest. L2 cache is on the CPU chip, but it is little larger and the slower obviously goes slower as compared to L1. L3 cache is shared amongst the CPU cores. It is largest amongst all and obviously slower than L1 and L2. Looking at just the description of how the structure of a cache and the main memory compare. Now, the cache memory and the main memory have to be the same size in terms of the transfer of data, because we cannot have bits being transferred from one side and blocks of words being transferred for the other side. Now, besides that, if you look at the cache, there is a field which is referring to as a tag. Now, this tag is used for the cache memory because this identifies that which block from the main memory has been brought into which part of the cache memory. So, to identify that, the tag bits are used, which I am going to discuss a little ahead further as to the breakup of the number of bits, how they are saved. Looking at the structure, the main memory we know can be considered as consisting of 2 to the power n addressable words, which each will have a n bit address. This is what was depicted in the diagram earlier. For mapping, we will have fixed length of blocks which are k words each. So, cache memory and the main memory would all have the same size, which is the k words. So, automatically m becomes 2 to the power n divided by k blocks is the capacity that it can store on the cache. Structure of the cache we just discussed. There will be C lines of k words each, which is the same size. Automatically C stands for cache and M is for the main memory. Cache is smaller than the main memory, which is was depicted to you in the earlier diagram as well. So, some subset of the block of the memory will reside in the cache. So, the entire block from the main memory is not moved here. Some part of the main memory, which is dependent on the locality of reference we just introduced few slides back, is brought into the main memory, and whenever it is required, it is first searched in the cache. If it is found there, is utilized. If it is not found there, then there is a process of bringing it back from the main memory into the cache and then making it available for the search. The tagline I just introduced, these are the bits which are used to identify a particular block from the main memory which is stored. So, to identify which part of the main memory has been moved into which part of the cache, the tag bits are used for that. How is it operating? I was just telling you about it. Some part of the main memory is brought into the cache, into some part which is identified by the tag. Now, if the system is looking for some data, it first checks the cache. If the data is found in the cache, we say a cache hit has happened because it was found and it is used from there, retrieved from there. So, this is the fastest because cache is smaller than the main memory. On the other hand, if the data that was requested for search is not available in the cache, then we say a cache miss has happened. When the cache miss happens, then we need the control is transferred back to the main memory, the content is picked up from there, brought to the cache, and then the search starts from there. So, automatically this takes a little longer, yet remember that now for the next search, this data has already been brought to the cache. So, the next time it is searched, a cache hit will happen and the next search will be faster. The cache includes the tags, as I have been repeatedly saying, to identify which block of the main memory is available in which slot of the cache. Look at this diagram. It just talks about it's a flow chart of what I explained to you about having a cache hit or having a cache miss. So, if you go straight down, if there was a hit, we just go find the data and the job is done. If there is a miss, then the data is looked up from the main memory, brought into the cache, the activity done and saved on. The typical cache organization. This is the exact way the cache is positioned between the processor and the main memory. If you look at it, the cache is connected with the processor with the buses, which is an address bus, a control bus and a data bus. So, there is activity happening between all three, yet when there is a data that is being looked up for, there is a connect between the cache and the processor through the control bus. Now, depending on the cache hit or a miss, if there is something that needs to be brought in, there is a data buffer that is there. The data has been brought in from the system bus and then made available to the cache. Similarly, it also has an address buffer to save the addresses of what is to be brought in the next. Looking at the cache design, when we started this, we kept in mind that cache memory was introduced to have faster memory on a lesser cost and a shorter duration of access time. So, we need to follow certain principles for design of cache. Most important ones that are used have been identified here. So, beginning from addressing. Now, if there is something that is saved in an address, how do we identify that? I have been talking about something which is called as the tag. So, between the processor and the virtual memory unit, the cache is positioned and it interacts between both of them. The addressing is helpful because it helps reducing the cache misses, improvises the speed and automatically uses the cache for the optimal usage. It maintains the balance between the hardware complexity and the access efficiency. Looking at the size is, there is no fixed size, there is no optimal size. It depends on what all are we looking at. So, there is always a way of weighing out what is the most important to us, which I have discussed earlier. Is it the cost? Is it the speed? What is that we are looking at? So, when we look at the cost, we know that cache is small enough to meet the cost of the main memory, but it is large enough so we can have the access time reduced. So, more is the cache, automatically the cost increases. When we talk about the speed, larger is the cache, it tends to be slower and it then loses the purpose of having a cache because we were anyways having enough data saved in the main memory. Now, the checking the cache always takes time, and yes, the larger is the cache, automatically higher is the time it is going to take for searching. So, speed becomes compromised, and also it depends on the size, will also depend on the availability of the area on the chip as well as the board. Another important aspect is the mapping function. When I have been talking about some part of or the few words or blocks from the main memory being brought onto the cache and the search being performed from there, what is the method that we follow? How do we decide of what comes in, which block is brought in from the main memory to the cache? So, we have to follow some function that is used, and that is called as the mapping function. So, let us look at the three methods that are usually used: the direct, the associative and the set associative. Direct is something that is very close to what our name is suggesting. So, we pick up one block from the main memory, and that main memory block can go only on a particular cache line. I will explain it to you better with the diagram that follows. So, if I say that block number 1 from the main memory can go only on cache line number 1 or line number 1. So, let us assume we are saying all odds to go on odd, all evens to go on even, or we can say block number 1, m plus 1, 2m plus 1, 3m plus 1, some formula we can devise. All these blocks from main memory will only move to line number 1 on the cache. The method that we follow is not random, it is a formula that we use, which is written here. I is equal to j mod m, where I stands for the cache line number, j stands for the main memory block number, and m is the number of lines in the cache. How do we do? The least significant W bits will identify the unique word. The MSB, which is the most significant bit, is divided into two parts. One, S bits, which specify the memory block, and S minus R, which is also used for the tag field. This is explicit from the diagram here. If you look at from the extreme end, which is the least significant bit, two bits are being used for identify the tag. As we said, the 2-bit word identifies which block has been moved here into the cache. Then look at the 8 plus 14, which is the 22 out of the 24. We divide into two parts, which is 14 bits and an 8 bit. 14 bits are being used to identify the line that is being used, whereas 8 is being used for the tag here. So, this is how 8-bit tag and a 14-bit slot is being used. 2 bits is for the word identifier. This diagram would be able to explain to you how there is a one-on-one mapping between the cache to the main memory. So, you see straight lines, same amount of block size, and each line just follows to the same line into the cache. So, if it is line number 1, goes to the line number 1 of the cache and nowhere else. It can either go there or nowhere else. Now, if this is how it seems the simplest method possible, it can also have its difficulties, because if you are following these formula for calculation, cache line number 0 can accommodate blocks number 0, m, 2m, 3m and so on from the main memory. Let us assume that the cache line 0 was being occupied by a memory block, say m. And the next search that we are looking for is a data that is saved in main memory block 2m. The 2m will also be utilized or be saved on the cache line number 0, which has already been occupied. So, there is going to be a fight for that same cache line. Now, this is a disadvantage. However, a simpler method was that we know which line of cache does the main memory block go. So, it is easier. However, if the cache line is occupied, then there is going to be a difficulty, and that is the disadvantage of this. So, pros and cons, if you look at it, it's a very simple method, it's the most inexpensive method. We simply use the formula I is equal to j modulo m, the block number is identified, line number is identified, and that block goes to that line. So, there is a fixed location for a given block. However, as I explained to you, if a program accesses two blocks that map to the same line, repeatedly the cache misses are going to be very high. So, to remove this disadvantage, we move to the next one, which is called as associative mapping. This will overcome the disadvantages of the direct one and have some amount of its own advantages. Now, here we will allow the main memory block to load into any line of cache, yet it cannot be any line. There definitely has to be some method that is utilized behind it, which is what we will just see. So, memory address is interpreted as the tag and the word like the earlier one. In this, it identifies the tag is doing the same job, identifying the block of the memory. Every line's tag is examined for the match. It requires searching the entire cache for a matching tag, making it slower, more complex, but reducing the conflicts. So, if this diagram, it clearly shows this one block of the main memory can go to any block in the cache. Yet, when it goes for searching that block, the entire cache has to be looked up for. So, we have avoided the clash if the line was occupied. However, now with the advantage of any free block being available, it can go and save itself, wherein when we are searching for it, instead of going to that one single line, now we need to start looking for the tags for the entire cache memory where there was a possibility of this one block of main memory being saved. So it's taking definitely longer time as compared to the direct mapping. The associative memory structure also utilizes a similar tag, a 22-bit tag and a word for 2 bits. 22-bit tag stored for each 32-bit block of data. We compare the tag field with the tag entry in the cache to check for the hit, because we are looking for some data now. The least significant 2 bits of the address identify which 16-bit word is required from the 32-bit data block, and that's how the searching happens. Just to summarize the associative mapping, the address length is s plus w bits. The number of addressable units automatically become 2 to the power s plus w, whereas in case of the direct it was 2 to the power n. The block size is equal to the line size, which is 2 to the power w, words or bytes. Number of blocks in the main memory would be the number of addressable units divided by the block size, which is 2 to the power s plus w divided by 2 to the power w, which gives us 2 to the power s, which is the number of blocks in the main memory. The number of lines in the cache is undetermined because we do not have to map one-on-one, and the size of the tag is s bits, because without these tag bits we will not be able to search for our data. Lastly, coming to the third method of mapping, which is between the direct and the associative, tries to take the advantages of both the methods and reduces the disadvantage of both the methods. So cache is divided into sets, and then each set will contain several lines. Here a memory block maps to a specific set, but within that set it can occupy any line. We are going to use the same formula of I is equal to j mod v from the direct method, and we are also using one more formula, which is m is equal to v multiplied by k. Now these two will help us identify which line goes to which block. So where the cache is divided into v sets and each set is consisting of k lines. It will be more explicit to you when I show you the diagram. A given block m can go to any line in the given set. So for block b, it can be in line of set I. Let's assume we are 2 lines per set. It's going to be a two-way associative mapping. Given block can be in one of the 2 lines in only one set. This is how it looks for an easy understanding. This is where we will see a part of it can move to the cache line set 0, or it can move to cache line set say v minus 1, but in a specific location. So this definitely reduces the deadlock that was happening in case of a direct. It reduces some amount of searching that was happening in the associative and is helpful in terms of getting a better utilization of the storage in the cache. So summary would be, address length would be the same as s plus w bits. Number of addressable units remains the same as s to the power s plus w words or bytes, and block size is equal to the line size, which is 2 to the power w words or the bytes, like we had calculated in the associative mapping. This is the similar way of calculating the number of lines that we are using, the number of sets we are using, and which line goes where. The tag bit remains the same to identify which cache line is saving which memory block. Now we are looking at saving something. We've already discussed how we are going to save or map the data from the main memory into the cache, but it's just not about saving the data there. We also need to retrieve it from there. Now when we are retrieving it, sometimes we may just use that data, or sometimes we may want to not use that data anymore and bring in some new data, because it cannot be left there for permanence. So there is going to be something called as a replacement algorithm. Replacement algorithm means that if I do not need some data in the cache, which is smaller in size as compared to the main memory, I need to remove that content or data from there and bring in the new data there. But what goes out is also dependent on how far we have used that which was saved there, or we just randomly picking up data and sending it out. That can cause an issue, because maybe the next activity involves bringing in that data again. So, we might have larger number of misses rather than having larger number of hits. So, whenever there is a new block that is to be brought into the cache, we use either one of the existing blocks to be replaced if there is no more space there, and there is going to be only one possible line for a particular block, which is like the direct mapping. We have no choice, so we need to remove that or replace that line completely in terms of the associative method. We will use two formulas, or rather two methods that we use more often, though there is a third one also. So, let us look at the associative and the set associative methods first, because the hardware that is implemented also has an algorithm to get the speed to it. The very first one is called as the least recently used, or the LRU algorithm. The name itself suggests the block that goes out is the one which was the least recently used one, which has had no reference. The next one we use is a FIFO, which is first in or first out, and hence whatever was brought in first goes out the first. The last one is the least frequently used, where we use a counter. We keep track of a counter, whichever has the least number of utilization, we throw that block out. And the last, of course, is a random, which is not based on usage. We just pick up any block, remove that, and bring in the new block there. Now, to write, we use two kinds of policies. One is how do we rewrite over them? Do we overwrite? Because every time we move in and out the blocks, the data in the cache as well as the main memory has to be updated at the same time. We cannot have different versions of the data lying at two different locations. So, the policies that we use usually cause issues, that there could be updations happening on the cache but not onto the main memory, or vice versa. So, we use a policy called as write through, where irrespective we make all writes to the main memory as well as the cache. So, at any given point of time, both of them are completely updated. Of course, this causes lots of traffic. This is because a lot of writing happening irrespective whether there was a change or no, and it can create bottleneck. The other one is a write back. This depends only when there is an update. So, we attach an update bit for the cache slot, which is set when the update occurs. So, only when there is an update that is happening in the cache, the main memory is updated. Automatically, it gets updated only when there is a change happening. So, there is not going to be too much of traffic there. The last, of course, is the line size, which is retrieve not only the desired word, but a number of the adjacent words also, assuming that the block size is going to be done things. So, larger blocks, we know data is overwritten shortly after being fetched. And that brings us to the end of this session, which is multiple caches can be used to bring about faster than the bus access, and it also utilizes the free buses for some other transfers. Thank you so much.